So we're going to do advanced interactions. We called the last lecture advanced strings. And now we're going to look at some other ways to do interactions with functions, definitions, and iterables. The first thing that we're going to look at is something called Lambda Functions. And this is taken from functional programming, from Lisp, et cetera. Just a very basic of what a Lambda function is well, the way to think about it, it's an anonymous function. It's a function that doesn't need to have a def in front of it, but you can still use it like it was a function. And these are, in some sense, like Lisp comprehensions are one-liners for doing for loops. Lambda functions are effectively one-liners for doing a little bit of something you'd want to do, math or string manipulation, et cetera. And then it allows you to use that in a very nice way. So here we're actually going to assign to the variable temp a lambda function, and the way that you wind up creating a lambda function is you say lambda, this is a protected word within Python, lambda space x colon whatever. Now you can have a number of arguments here, but you could say x comma y, and a way to think about this is if you were going to do this as a function, you might say myfunc x return x squared. This right here is identical to what this is right here, okay? And in fact, what you could do is you could just say temp. The type of what gets returned is of a function when I create the lambda function, and I can use it just like I would any other function. So I get back what I expect. But again, we don't have to actually name that function. We don't even have to assign it to a variable. I can just have this lambda function whose job it is to take two arguments, x comma y, return the square of the first one, and then add on the value of the second one. And then I can just directly apply it with 2 and 4.5. So let's do the math in our head beforehand. So this should be 2 raised to the 2 is 4 plus y, so that should be 8.5. And we can just change that here if we want. Okay? So here we've created a function without a def, and we've applied it on a single line using some real data. We can have lists of functions, because again, these are all just objects anyway, so we can have a whole bunch of lists of anonymous functions. So this first function, it takes the square, the second takes the cube, the third one will do, let's see, so it'll take the square root of the argument as long as it's greater than 0. Otherwise, it's going to say, really, did you really mean to do that? And now I can loop over that array of lambda functions, and I can apply this number and see what I wind up getting out. So I get the square, I get the cube, and then I get some reasonable output for that. So everyone see that we can use lambda functions. Really, again, they're considered sort of anonymous and short one-liners. If you're going to need to make print statements out of these things, or you're potentially going to wind up doing a bunch of stuff inside of one of your functions, a lambda function is not what you want to use. Again, it is for those kind of one-liners. Any questions about that? Now, going back to the second breakout of yesterday, we have, as you'll remember, this airports dictionary and the flights list, and we asked you to print things out. Here, if we looked at sort, we already showed you yesterday this reverse keyword, and I told you that today I would teach you about this keyword. Key is something that says, what am I supposed to be looking at in every element so that I can compare each element to all the other elements? And the default, if you don't give key, is that it's going to look at the first element. So if I sort without a key, I basically will sort alphabetically, although as we saw yesterday, somebody pointed out that even though S comes, Yes, even though s comes after n, because s is capitalized, this is just how Python string comparison winds up working. It considers a capital S coming before a lowercase n. But if I now give it a key and say, no, 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 I don't want to sort on the first thing, I want to sort on the fifth element, what I can say is every time that sort winds up saying, okay, what element am I supposed to be looking at now? Instead of it looking at the default, we're basically going to say, no, no, look at this one right here if I want to sort by time. 6, 5, 1, 9. So instead of doing that very, very long, complicated solution that we showed you yesterday, where you had to by hand go through and make a new list of all the different flights, or make a new list where you switch the ordering and then you just use the normal sort, now you can use these Lambda functions for things like this, for creating these keys. And I didn't have to have a new function that did that. Any questions? Yeah. So that's a good question. What if we wanted to actually do it alphabetically, but we didn't want to, so we wanted to essentially override the way that it was doing sorting now. So in that case, you would do x0, so get the first element, and return the lower of that. So let's see if that wound up working. United, there it is. US Airways comes after United in many ways. Yep. Key is always going to wind up being defined a function, I believe. I think if you just said key of 1, it wouldn't work because it's not callable. So it has to be callable, which isn't strictly a function, but you should consider it a function. No, because you're actually trying to sort on this list right here. And so where you'd give it the list is in the thing that you're trying to sort. Yep. There is a way, there's something called an item getter, which is part of the collections module, but all that's doing is it's getting the item for you. This is a function because we're basically creating the getter that gets us the element that we actually care about. And because, so we couldn't say, for instance, key equals x dot get 4, because x isn't defined here. The Lambda function is the thing that winds up defining the x for us. All right, and by the way, it's kind of ugly when we print it out like this. So there's another module which we'll introduce to you here called peepprint, which makes pretty printing versions of things. So it just prints out JSONs and nested dictionaries in a slightly nicer way. Here's the item getter where you say, okay, I want to sort on the last element, so by time, and then I want you to sort on the flight number, and then I want you to sort on the airline. This is, again, not something that we would have asked you to know about for the second breakout yesterday, but if you look at this operator module, it's actually quite powerful. There's also a related one called collections, which is also very useful for doing permutations and combinations from lists. Filter is another thing that we can use. It's similar to what you already wind up getting inside of list comprehension, so I won't spend a lot of time. Remember yesterday I showed you list comprehension when we wanted to get all the numbers between 0 and 100 that satisfy the condition that the first and the second bit were both 1, and it was not divisible by 11. So we got this out. We can also create a function that returns back the truth value of whether that is for a given number, whether it actually satisfies that condition. And then we can apply a filter over all of the numbers. So this is some iterable in the second argument, and the first one is a function. And what filter is going to do is run through each of the elements of the second argument, apply this value of whatever comes back, apply this function to that value, and then if it comes back as true, it's going to keep it. If not, it's going to wind up removing it. So if I do that, I should get the same answer out. Okay, so this doesn't have to also be, exactly range. We can put in whatever numbers we want and ask that question for ourselves of this iterable. Okay? Yep.
So if you then took that filter and applied it to another list of the same length, it would pull out the same element numbers, not that they would necessarily satisfy the numbers. Keeping a mask or an index of where that would.
Yeah, so if I said filter f on the result of that, I get back a filter, which is itself an iterable. If I did a list of that, I'll get the same thing back out, because I'm just filtering it again, same number. I'm not sure I'm answering your question.
Well, sometimes you want to perform this filter on this array and
Yeah.
use the same filter on other arrays that are the same length.
Yeah, so this won't return back to you the indices that it used to do the filtering. If you wanted to do that, the easier thing, in my mind, would be to use the list comprehension, and instead of returning back the, well, in this case, we're looping over numbers, so it's the same as the thing we're looking at. But if I ranged from 0 to 10,000 or negative 10,000 to 10,000, instead of doing range, I might do enumerate. So I'd actually save the index over which I looked at it, and then you could return the tuple of the index and the resulting value, and then use those again. Probably, though, because I happen to know what you work on, you're going to wind up working with large amounts of arrays of images and potentially time series data. There you might want to, instead of using the native Python stuff, you'd want to use NumPy and use like the args within NumPy, so argmin, argmax, or the where function, which is similar to what you have in IDL. So there's an np.where, which grabs for you wherever the expression that you give inside of the parentheses is true. Okay, so I can also create a Lambda function to do the same thing using something called map. And this is a little bit weird here. We're going to wind up mapping against this range, which is basically, a map is applying a function. In this case, we're applying a Lambda function. And we're not explicitly saying that the result should be true or false. We could actually set this to be a Boolean. And we see a bunch of places where it's false and where it's true. I'm going to show you map in just a little bit, but this is another way to do what we just did. Let me just quickly show you, if the input is a string, that the output would also wind up being a string if we wound up doing our list comprehension. Here I can wind up joining to get a string back out if I want to actually get not a list, but you see here what's happening is, because I did a list comprehension, I wound up returning back an iterable, which is iterable over numbers, and then I wind up joining those by this comma space. Okay, so map is another way to do list comprehension. I sort of cut to the chase, or at least showed you quickly that we could use map that gives us a similar result. Let's see what map actually does. I use map quite often, and I don't use filter very often. In fact, most of the times when I'm trying to do a filter, I'll just figure out a list comprehension that gives me that filter. But map is very useful because now I can create functions, and then I can apply that function sequentially on something that is an iterable object. So if I have a list, if I have a string, I can go to each character. Here I'm going to create a map where I'm going to say use the function times 3, and I'm going to loop over this string. And I'm going to loop over the characters of that string. Yeah?
I was going to ask, if you have a function that has multiple inputs,
Yes?
is map smart enough to know how to assign things in the subsequent list to those inputs?
The question is, if you have multiple inputs, does map know what to do? I don't know. We can try. I think it won't. I think you'll have to basically know that you're going to say give it a tuple of length 3, and then inside of the function that you're mapping, you'd have to say use element 1 to do this, use element 2 to do that. We can give that a try in just a second, but everyone see what this is doing right here? We'll come back to that. Has everyone seen a map before? So I've taken an iterable, in this case it was a string, and what did I do? I returned 3 times that. So I basically looked at every character and multiplied it by 3 times. Yeah.
So is this more efficient than doing a list comprehension?
The question, is it more efficient? I don't know. We can try. So how would we do that with a time it? So that was 1.6 microseconds. Actually, let's just save this here. So the question is, could we use a list comprehension instead? So here, what would list comprehension look like? How would I write that out? So times 3 of x for x in spam. So do I get the same result? Yep, so let's time it. I don't know the answer, but we'll know in a second or two. Okay, so 1.1 microseconds. To me, it looks like it's probably about the same. Probably we should be fair and just not redefine the function 100,000 times or a million times. See what we get there. So that was, again, about the same. It looks like it might be slightly slower to do that. And it will probably be dependent upon how many elements that we have here. So if instead we said range here, you notice I'm doing stuff in the notebook while the kernel is still busy. So that was 19.6 milliseconds. (17.1). It looks like the list comprehension is slightly faster in both the small amount of data and large amount of data case, but not enough that you would do one or the other if you fancied one. And as you saw, we don't have to just loop over strings. We can loop over numbers, etc. Remember yesterday when we introduced NumPy, if you created an array going from 1 to 10, well, let's try this now. So if we said range, and we created a list out of that, does it make sense to raise that list to the 3rd power? No, Python doesn't know how to do that. That's why we needed the map. What NumPy is actually doing, let's try import NumPy as NP. What NumPy is trying to do is do that for you. That's 1 to 10. So there we go. We've got the numbers. And now I can raise it to the 3rd power. It knows how to do the mapping for you on array types. So that is typically how you'll wind up interacting with data, is using NumPy and not doing it with lists and maps. But again, maps can be very useful. So for instance, getting back to a question on regular expressions, if you had a complex question you had of a whole list of data that you pulled in from, let's say, a large file, you might want to run a regular expression individually line by line. You could apply the map on the regular expression to each individual line without having to create effectively a for loop. Yeah, was there a question? Yeah, so you mean up here, like instead of saying spam, so let's see if this just still works. So instead of saying that, if we had said spam eggs Hillary, it would loop over each of the individual elements and multiply them by 3. Yep.
So map and filter both take a function and a list, and then return a list that meets that condition.
Yes. No. So filter will return only the items from that thing that's iterable, the second argument, where the function evaluates to true on those, and map will return every single item, which is just the evaluation of that function on each of those items. And it doesn't, to be clear, it doesn't have to just be a list, it can also be a tuple, I believe. So anything that's iterable. What? Can you iterate over file content? No, not using map. You could use what's called a context manager, open up a file, and then inside the context manager just do effectively a read on each line and then map over the read. But you couldn't loop directly over the file. You have to loop over the read method on the file. Yeah. Yeah. Okay, any questions on that? So if you, for those that know some advanced interactions, you've got map and filter. There's also this notion of reduce. So reduce takes a function and also a sequence and returns a single value constructed by calling the binary function on the first two items of the sequence and then on the result. So this is an accumulation function that says take the first two elements of the sequence, do something with them, take the result, and then do it again to the third element in that sequence and keep going until you run out. So we use this thing called functools to get the reduce. And here, what are we going to do? We're going to add numbers sequentially, going from 1 to 10. All right, get rid of that. That's 55. 5,050, that should be familiar to all of you. So what did we do here? We basically created a range, which is an iterable, and what did the reduce thing do? It said, okay, well I have this function, it's a Lambda function, I could have named it if I wanted to. Take element 0 and 1, which happens to be the values 0 and 1, or actually in this case, since we're starting off, it'd be 1 and 2. Add those together, the value of that is 3. 3 becomes the new x the next time I call this, and then I'm going to add the next one, which is 3. So now I'm getting 6. That becomes the new x, et cetera, et cetera. Keep going until you finish. All I've done here is just create a summer, a cumulative sum over all of those numbers. I don't have to do it on numbers from 1 to whatever. I can do it over anything I want to. So yeah, so that is a good question. Why do I get a different answer whether I went from 11 to 1? And that's because I also added this number 11, that's all. And I ended with 2 and not 1, right? Because I went backwards. This should give me the same answer. Okay. Any other questions? Yeah. It's not recursion because it's not calling itself. It's not calling versions of itself. It's looping. It's actually just looping. It's another, in some sense, it's another kind of mapping. But instead of returning results at each place where it did the calculation, it's only just keeping track of the results until the end. But obviously, like I just gave you a trivial example. What we're doing is we're summing numbers from something to something. There's a built-in called sum. And that thing is really fast, or it should be really fast. So that was, wow, devilish number of 666 nanoseconds. We'll try it here. The same thing. I believe this should be longer. Yep. Well, the plus equals operator, you'd typically be operating on a single variable and you'd be bumping up or down its value. This would be where you would wind up accumulating some interesting math number by number. So if you're trying to add the square of the numbers plus the next number, it doesn't have to be this. It can be something else because that's what you needed for your algorithm. Okay, now let's go into this notion of zips. And zip is a built-in function as well that comes with Python, and it's for doing pairwise concatenation of iterables and returning the result in the form of tuples. So if you've got a bunch of things in one list and another thing in another list, instead of having to do a for loop where you wind up bringing those two things together, you can just do a zip that just says, okay, take the 0th element of list 1 and list 2, and then put those two together and return a tuple, the first element and the first element, and put those things two together. So here I've got two iterables, two lists, I, you, and them, so 3 elements here, 3 elements here. And what do I get back? I get a list, which is a tuple, a list of tuples with 2 elements, I spam, you equals eggs, them equals dark nights. And it doesn't have to just be zipping up 2 lists. I can also zip up multiple lists. So if I zip this, and now I add some punctuation at the end, I get a list of 2-element tuples. No, 3-element tuples, because I gave it 3 lists. And here, I've got 3 elements here, 3 elements here, and 4 elements here. Let's see what happens. What happened is you notice that this blah got left out. So Python said, okay, I've got a 0th element, I've got a 0th element, I've got a 0th element, good, let me make that a tuple. I've got a first element, first element, first element, let me make that a tuple. Hey, I've got, this other one has 4 elements and the other ones don't, I'm done. So if it can continue to zip, it'll zip. If not, it'll just drop off the data that it can't actually zip up. I can obviously index into this thing. Oh, but I can't. Why not? Well, the first thing's a list. Right. So the first thing is a list, and I could certainly, if I wanted to, say the first thing is eggs. But now A looks really weird, because I can just assign, remember, lists are mutable, so I can assign different elements within that list. But when I did this, actually, let's say 1. I can't because I'm trying to now index into this and change that, and tuples are immutable. Okay? All right, so why is this useful? We've got questions, we've got answers. So what's, if we have a name, quest, etc. Now I can zip that up. So instead of having to loop over an index, I can just loop over the tuples. And I'm going to unpack those tuples in place when I wind up looping through the resulting list. So what is your it is? What is your Lancelot? It is name. Oh, wait, that's not what I wanted. What is your name? It is Lancelot. What is your quest? It is Holy Grail. What is your favorite color? It is blue. Yeah. It'll broadcast in what sense?
So, say you have a single column for X and then like multiple columns for Y. Would it put X with each column?
No, so it won't broadcast the way that NumPy would broadcast. So the broadcasting thing is purely a NumPy thing. Python won't do that. Zip will just look at the first element and say, okay, we're good. We've got X, that's 1 element. Next one, oh wait, none of them, there are no more elements in X. I'm not going to do anything anymore. Okay, so this is quite useful. Hopefully you can see how you might make use of that in some of your functions. Any questions before I move on? Okay. So now we're going to do the try except finally. So now we're going to start dealing with the case when things go wrong, or potentially things go wrong in a way that you anticipated, and you might want to deal with those gracefully rather than have your program halt. Python tries not to segfault, and typically if you get a segfault with Python, it's because you're calling a third-party module that wasn't battle-tested in some way, and you access some memory in C incorrectly. It's very, very hard to make Python itself segfault. Brett's laughing at me because it's actually happening to him now. But so the way to think about these try, except, and finally statements is a way to wrap volatile code in a try statement. And when something goes wrong and an exception is raised as part of that, perhaps you try to open a file that didn't exist, perhaps you divided by 0, you can actually catch those and deal with the results gracefully. So let me see if this works here. Here's what I think of the try except statement. Anything you wrap in a try statement, this is from Saturday Night Live, if it comes up. I think it's right here. It's like a Jeopardy-like thing. All right, so you'll see what that means to me in a little bit, but the way to think about it is everything that's in the try statement, even if it fails, your program isn't going to crash. And so one of the tempting things to do is just wrap your entire program in the try except statement, and then you know it's definitely going to work, right? No, that's not obviously the case. Try except statements are very powerful, but you want to use them quite sparingly. Because in many cases, when you're running a program and something happens that you weren't expecting, there's an edge case that you didn't think of, you kind of want an exception to be thrown and you want your program to stop, because that's a good place for you to say, aha, I didn't anticipate that. If you wrap your whole program in the try except, like making the whole airplane out of a black box, it's probably not going to fly. And you're going to wind up having issues that you're going to wind up regretting later on. So let's take a look at the use of that. So remember, we had the ability to get raw input from end users and assign that to a variable. We'll just multiply that result and raise that to the second power and print it out. So enter a number, and I'll square it. So 2, that looks good. Enter a number, and I'll square it. Spam. What happened? And we've been seeing these error messages throughout the boot camp. What did we do? We actually raised, or Python did for us, the interpreter raised what's called a value error. And this is an exception. And it meant, and the reason why I got a value error is because it couldn't convert a string to a float. And that string was that. Instead, let's just use this try except, where we're going to wrap volatile stuff in here. And it's volatile because an end user who isn't you is going to wind up interacting with your program. And if something goes wrong, I'm going to wind up catching that problem. And then no matter what happens, I'm just going to have what's called a finally, which is sort of the cleanup part of a try except statement. So we'll execute that. So I've just created a function f. If I run it, enter a number, and I'll square it. So 4.0. That looks good. Thanks for playing, because I executed the finally. Let's try spam. Dude, I asked for a number, and spam is not a number. Okay, any questions about the very primitives of using try excepts? Yeah.
Well, I'm just curious if there's a preferred approach. It seems like using this would be a lot more efficient than, saying, trying to pre-evaluate whether it is a num, and you do all the checks ahead of time, but you have to execute that code every time, especially if you're reading data.
That's a great question. Is it preferable to try to do all the truth testing on what you actually just got, relative to the question we had earlier this morning about if I got a string, is this thing that's representable as a digit? I don't think there's a best practice around it. Again, I try not to use try except statements unless I really know that I've got a volatile piece of the code, which almost always is because I'm talking to the outside world. If it's data that you own and you control and you created and you're manipulating it, if something goes wrong, you probably want to know about it. Because the problem with the try except statement is you wind up, in some senses, hiding what went wrong. And we don't know why we got in here. And this is because I basically caught all exceptions. There are other types of exceptions that perhaps I actually didn't want to catch. and I wanted to actually throw an error back up to the running interpreter and stop. So my answer specifically for the way that we've constructed this particular problem is that probably it's fine to just do this as a try except because you're interacting with the outside world. If it's a function that you built that's sending data to another function, and that second function needs to test whether all the data is, not negative, you probably want to just do that and try it out yourself. Again, if you hit an edge case that you weren't expecting, you don't want to be in a try except statement that doesn't wind up allowing you to see what happened. Yep. Yes, there are lots of exceptions. We're going to see many of those. And we'll see how you can actually catch different types of exceptions in different ways.
So in the case there, if you gave it a large enough number that squaring would generate an exception, that would be undifferentiatable from...
The way that I've called it, it'd be undifferentiatable from it. Now we're going to see it probably actually segfault after I... Oh, actually, it's okay. Wow, that's a big number. Wait, what if I did? Okay, this is probably ill-advised at home. Do not try this. Wait, let's do 1 exponent 360. I got infinity. So raising a number, a very large number, and squaring it, for this version of Python decided not to throw an arithmetic error. Somewhere in some specification it said, if I get a number that's larger than my largest number that's representable by the number of bits associated with a float, if it's larger than that, don't worry, I'll just call it infinity. But certainly, as we'll see later on, if you had a 1 divided by 0 in your, let's see if we did this. So that will wind up throwing an exception. Oops. Oh, I didn't execute this? There you go. Huh?
That's correct.
What?
That's correct.
Yeah, but it didn't...
But it brings through.
Oh, yeah. Sorry. There you go. Thanks. So it did throw the exception. We didn't see what type of the exception it was. And I'll show you later how to actually show that. Yeah.
This is the point because if you want to keep the exception, you can put raise in the except block, and it'll re-raise your...
Yeah, that's right. So there is a way to re-raise the exception that you got. So I got a 0 division error. Yep, thanks. Now, if I really wanted to, jumping a little ahead, I could capture, what was the other exception we had before? Value error, thank you. I could capture a value error and re-raise it. And here I could capture a 0 division error and say something else. And here I could capture all the other exceptions if I wanted to and raise that. That's typically what you'll wind up seeing in many Python programs is you'll catch the errors that you know exist, and all the others you'll basically say, that's no good. So I divide it by 0. Okay?
The percent that you have in your code there that you're pushing the temp back into the string in there, what's the S, the percent S?
Oh, %s is just the old school string way of putting temp here. Okay, so I can have a try statement without an exception. So this is where I don't actually catch the exception, but I sort of do some cleanup afterwards. That should work. So here I said eat at Joe's. Oh wait, that didn't work at all. That's okay. I raised an exception, but even after I raised the exception, I still said bye. And you'll have to think about how you would wind up using this. Now notice if I didn't have the finally, I can't have that. I can't have a try statement without either an except or a finally. So you have to have something after that. So a try statement by itself doesn't make any sense. Control Z. And then we just do a pass in here and see what happens. So you notice I didn't get the by, and that's because when I raised the exception, I just stopped. And even though there's a print by at the end here, I haven't gotten that far in the program because the interpreter just stopped and said I've got an exception. So if I really want to say goodbye, or let's say close down a file when an exception is raised, I have to put that inside the finally. Okay, so we're going to work on some things now that'll help you for the breakout. You can actually dynamically create Python code and then have Python execute it for you. So at runtime, you can create strings which look like Python code and have Python execute that code. It's kind of a nice thing of not having a compiled language. So we're going to print check it, and we'll just print, and we'll create a value A, which is the string representation of that. And that's just print check it. So that's just a string. But now we can use this thing called exec, which is a function that operates on strings, and it winds up assuming that those strings are Python. So we're executing that as if it was Python. Check it. Now we'll create a new string where we say x is equal to 4.56, and we'll execute that. And now we'll print x. So now x is in my namespace. I can delete x, and I can now print x. What do you think happens? It's not in my namespace anymore. So this is very interesting. It means you can have Python create Python code. And that becomes very powerful. Now, let's see if we can do some interesting stuff with that. So we're going to create a little program here that will take the input from the user, and we're going to say, what function do you want me to rename that's in the namespace? So if I have an and or I just give it nothing, I'll just break out of that. What's the new name of what you'd like to give it? So I'm basically going to, and this is very unsecure, so don't put this on the web. Just do this on your laptop. I'm basically going to say, do whatever I said over here, and then set that to whatever I said over here. So you'll see what I mean. So what function would you like me to co-opt? Math.sign. And what is the new name you'd like to give it? I'll call it JSign. What's another function you'd like me to co-opt? Print. And what do we want to call it? Write. Okay. And then I'll end. So now I can do JSign of math divided by pi. There we go. So now you want me to say write hello. Now remember, we've been assigning variables to other data structures that are also pointed to by that variable. You can just call this one function whatever else you want. Remember when we did import, from NumPy import this as, that's where we're basically saying, even though in its own namespace it was called the sign function, now call it whatever I want in my own namespace. I think we called it the Wicked Awesome Adder last time. So what did I do? I dynamically created Python code that said set this variable to equal to this variable. So it doesn't just have to be functions, I believe. Let's see if this works. Any questions about exec? Please don't write code and then expose exec to the web. You will lose everything, or worse. Yeah.
You need to close your kernel, and all that stuff disappears, and the old names come back next time.
The old names come back. So the namespace thing with JSign and Josh Pi and all that stuff and write, that only exists in the current namespace, which is part of what the current interpreter, which is running their current kernel. If I wind up restarting the kernel, and then I run this, It doesn't know what that is. Any other questions? Okay, so now there's another thing which is similar to exec, but now you're evaluating expressions and you're returning the results back into Python land. So rather than doing an exec and assuming everything there is Python code, you have just expressions, and you're taking the results of those expressions and you're assigning those back to variables. So eval 5 should be 5. Eval, where I now have the value of x, which is 5, and I put it in here, that's just 5 plus 6, that's 11. If I take the absolute value of minus 100, that's just 100. Eval if 1 colon x equals 4 doesn't make sense at all because this is a statement, it's not an expression. What's that? This is, yeah, a good way to think about eval is sort of a one-liner Lambda function. I often don't use eval. Typically, I'll just use exec. Okay. It is, that's correct. Okay, so this is hopefully going to be a fun breakout session for you all. We're going to write code which generates Python code that approximates the function x squared plus x. So this is effectively like poor man's genetic programming. So what's going to happen? You're going to randomly generate Lambda functions using a restricted vocabulary. So for instance, x, spaces, pluses, minus, 1, 2, 3. And you're going to evaluate those Lambda functions at a fixed number of x values and save the difference between that and what the objective function, which is x squared plus x. And you want to catch errors. So what's going to happen is, what does it mean to randomly generate a Lambda function? You're going to basically create a string which says lambda x colon, and then random strings after that. And you can draw those random strings from this vocabulary right here. Okay? And so sometimes those will actually, when you do exec on those will actually evaluate to be proper Python. Sometimes it'll be garbage. You'll say x plus x minus 3 plus space, whatever. And that won't evaluate to be correct Python. But every now and then you're going to randomly wind up creating something that looks a lot like x squared. It might be x plus x, which is 3x, which is close to x squared, evaluated in certain places on the number line. And then you're going to wind up basically finding that if you do a large number of iterations where you're randomly creating Python code and you evaluate that Python code, that you're going to wind up just getting x squared plus x. So the start of the file should look something like this. Import the random module within Python, import numpy, create a vocabulary. And if your vocabulary is very large and you have sine and cosine and all that stuff, it just means it's going to take longer to find the random time when you actually create the right expression. But if you do it about 1 million times, you should get x squared plus x a couple times. Total number of characters in your random lambda function should be about 10. And you can evaluate this wherever you want. You know, I'm just doing it around 0, so from minus 3 to 3 with steps of 0.4. And the evaluation that you're looking at, the values that you're looking for is just x squared plus x. And you're going to loop over the number of tries and then save the results. So here you're going to wind up using lambda functions. You're going to wind up using the random module. You're going to wind up using try except. Because if you're trying to run a random string that may or may not be valid Python, you're going to throw lots of exceptions.